The first sorting algorithm that we will see is selection sort. You probably have seen this selection sort algorithm in COMP150 because this is one of the easiest algorithms for sorting, very intuitive and usually used as an example when people teach COMP150, the Introduction to Programming. So what is the idea? The idea is that you look into all the items in the array and find the smallest one, put it as the first item in the list. Then look through all the rest of the items, find the next smallest one, basically find the smallest one among the n-1 item and put it as the second item in the array, and just repeat until you put all the items in place. So let me actually show it to you over an example. This is the original list that we have. We look for the minimum item over the list. The minimum item is 8. You swap it with the index 0 or the first item in the list. And so 8 is at its position. Then you look at all the items at n minus, the remaining is n-1. Here you have actually n items, right? Find the smallest item among n items. Here you find the smallest item among n-1 item. The next smallest item is going to be 14. You just swap it with the 17 and put it as the second item in the list. Then you find the smallest item among n-2 items. The smallest item is going to be 17. You put it as the third item in the list. Find the smallest item among the n-3 items and put it as the fourth item in the list. And the last item will be actually in place. So that's it. This is going to be the idea of the selection sort. I can actually show you how to implement this. But just before go to implementation, I think this is very intuitive what is going to be the time complexity. In the first step, you scan the n item to find the smallest item, right? Which actually take n, you need a loop that iterate over all the items. That loop will iterate n times. In the second step, you need to find the smallest item in n-1 item, find the smallest item in n-2 item, and so this is going to be just the summation of all these numbers, which is going to be this summation, which is clearly the O of n power 2 or theta of n power 2. So if I'm going to show you the code, a simple Java code. The argument that I pass to this method is an array. You can see that I have written it as comparable. So all the items in this array, we don't know what is the type of the object, but we know that they are comparable. So if I wanted to actually to compare these objects, I can use the method compare to. This loop here is just this inner loop will find the smallest item. This loop here, just check that this is the outer loop that tells you that, okay, when j equal to 0, you are looking for the smallest item to put it as array index j. So in the inner loop, you will find the minimum item, and at the end, you just swap the item at index min. You see that I didn't find the item, I just find the index. Basically, this is equal to finding the item, but in terms of the implementation, instead of exactly finding the objects, just keeping the object, I'm keeping the index. So min is of type integer and basically tells me that where is the index of the minimum item. At the end, when I know that where is the index, I can swap the index of min. So basically here I am swapping array index min with array index j. So at first, when j is equal to 0, you put the minimum item. When j is equal to 1, you put the second minimum item. And here, this loop, you will see that the limit, the boundaries of this loop. The inner loop starts at j plus 1. So if you are looking for the minimum item, you start at the min index from index j. So you started from index j plus 1 to the end of the list. Compare each one to array index min, and whenever the item is smaller, you just change the index min to be index I. It means that the item at index I is smaller than the item at index min, so you update the index min. So what is the time complexity? Here, I mean, we have already actually discussed the time complexity. I just wanted here to show you that it doesn't matter what is the order of the item in the original array, the time complexity is always going to be n power 2. So for example, if the original array was already sorted, something like this, that the original array is just 1, 3, okay, for example, 5, 6, 7, 9, and for example 10, already the items are sorted, right? But you always iterate through this loop, right? And you always iterate through this loop as well. There is no condition that you actually force you to don't iterate. The only part that you can actually either iterate or not is this specific statement. So at the end, this condition and this loop will iterate always. So in total, the time complexity will always be n power 2. It doesn't matter how many times you would actually execute this line. Anyway, the time complexity in the best case and in the worst case is going to be n power 2. The worst case and best case are equal. So in that case, we don't need to check the average case. Definitely, if the worst case and best case are the same, the average case is going to be equal to the same, the worst case and best case. So we are done with the time complexity of the selection sort. Best case, worst case, average case, it always works in n power 2, and we cannot make it better than this. The other thing about this sorting algorithm is that, as you can see, if you check the algorithm, you will see that we are not using an additional memory except some except some local variables. I'm not creating another array of size n, or for example, of size n divided by 2. So the amount of space, additional space that I am using doesn't depend on the number of items that you are sorting. If you are sorting 1,000,000 items, or if you are sorting 1 trillion items, if you are sorting only 10 items, you always just use these 3 variables plus 1 variable here. So just 4 additional variables. The time complexity, the space complexity doesn't depend on the size of the input that you are sorting, so we will say that it is in place. This is the good thing about it, but of course the time complexity was not really good. We will see that there are, I should say that they are not good. We will see that there are way better sorting algorithm than selection sort. The next sorting algorithm that I'm going to cover is called bubble sort. So the idea of the bubble sort is that we started from the beginning of the list, and by just checking, comparing each item to the next item, we would say that, okay, just try to bubble up the largest item to the end of the list. Okay, so instead of, unlike the selection sort, that you find the minimum item, or you can actually do it in a reverse way, and you find the maximum item or minimum item, here we just bubble up the item to the and force it and make it to move toward the end of the list. Okay, so after the first round, the largest item will be moved to the end of the list. Let me actually show you the how the bubble sort works, and what do I mean by bubbling the largest item to the end of the list. So just assume I have an input array like this one. This is the original array that I have. Okay, and what I am going to do, I'm going to just show you what is the first round of this sorting algorithm. I'm going to bubble up the largest item to the end of the list. So what we do here, the size of the array is going to be 6, right? And J basically tells me what is the index of the largest, what is the last index of the array. Okay, so J is equal to 5, basically tell me that this is J. This is going to be the index that I am looking for. It tells me that I wanted to bubble up the largest item to end up and sit at index J. What I'm going to do is that I'm starting from I equal to 0 and compare the item at index I with the item at index I plus 1. Okay? By just comparing these two items and check that if the item at index I is greater than the item at index I plus 1. So let me actually show it to you what is going to be done here. For I equal to 0 until I is less than J I plus plus. This is actually something that I am doing here. I wanted to always compare the array index I with the array index compared to array index I plus 1. If array index I is greater than array index, if it is greater than array index I plus 1, I would swap them. So just use some comparable temp. Just swap So you see that here in this actually 3 lines, I just swap array index I and array index I plus 1. So in the first round, when I is equal to 0, you compare I equal to 0 with I plus 1, index I with index I plus 1. So this is not a smaller, so you see that I'm not doing any swap here. In the second round of this loop, when I is equal to 1, you compare the item at index 1 and compare it to the item at index 2. Basically, actually, they were the item at index 1 was greater, so you swap the item at index I and the item at index I plus 1. So you swap 14 and 12, right? And then you compare the item at index I for I equal to 2 with the item at index I plus 1. Is it greater? The item at index I is greater than the item at index I plus 1? No, this is not greater, so we don't swap. Then you compare the item at index 3 with the item at index 4. Because the item at index 3 is greater, you swap them. then you compare in the next round, you compare the item at index 4 and the item at index 5. The item at index 4 is greater, you swap them. So you saw that in one round of this loop, the largest item moved, bubbled up to the last index, which was index j equal to 5. If I repeat this, for example, if I make j to be equal to 4 and run again, run the same loop, you will see that in the second round, the next largest item will actually end up to the index j equal to 4. If you repeat it and run it for j equal to 3, the third largest item will be moved up and sit in the index j. So basically we just, whatever I wrote here, I just need another loop on top of that just change the value of j starting from the last item, j equal to array length, whatever is the last item, -1 until j is greater than 0. Basically, because when j is equal to 0, this is going to be the smallest item. It is already in place. So this time j minus. So I just need to put this loop, and this is going to be the full algorithm, which I am showing it to you here. You see that this is exactly the loop for j, this is the loop for I, and this is that if statement that compare array index I with array index I plus 1. If array index I is greater, you swap them. Okay, so this is the full algorithm. And here it actually shows you all steps of the sorting algorithm, the bubble sort. That bubble, each time it bubbles up the next largest item and put it in its correct position. So now my question for you is, what is the time complexity of this sorting algorithm? And is there a best case or the worst case? What is the best case? What is the worst case? Are they different or they are the same? Like for example, for the case of selection sort, it doesn't matter what is the input. In the case of selection sort, the time complexity is always n power 2. If you look at the code that I wrote here, this loop will always iterate, the outer loop. How about the inner loop? The inner loop always will iterate as well. Although there is an if statement, that the inner side of the if statement might iterate or not. Some cases you might not actually swap, right? But the if statement will be executed as well. So the if statement, you need to compare I with I plus 1, the index I with index I plus 1, in all of the iterations of the inner loop and outer loop. And this is clearly two loops that iterates for the first one. The inner loop will depend on the outer loop, but at the end, the total time complexity is going to be theta of n power 2, because it just iterates 1, 2, 3, 4. And so this is going to be the summation of 1 through n, which is going to be n to n plus 1 divided by 2. This is going to be n power 2. So the best case and the worst case for this algorithm is going to be n power 2, because you always actually iterate. You don't care if you swap or not. The time complexity, you still actually need to iterate. But one thing that I can do to modify this sorting algorithm and get a better best case is this modification that I'm going to show to you. Just assume that after this algorithm, this example here shows you um, uh, 4 steps of the bubble sort. In the first round, the largest item will bubbled up, which is, for example, going to be 9, and it will end up at the index, at the last index. In the second round, the second largest item will be bubbled up, and it will be stored at the index n-2, for example. And in the third round, the third largest item, which is 7, will be bubbled up, and it will be stored at the index n-3. In the fourth iteration, the next largest item, which is 6, will be bubbled up, and it will be actually inserted here at index n-4. Now you can see that all the elements here, the rest of the item, they are also sorted. So do I really need to continue the algorithm? No, right? You can actually stop the algorithm here. But the algorithm that I wrote, there is nothing that can actually tell you that, okay, you are done, everything has been in place and you don't need to continue. So I need to update this loop so that if I know that already all the actual items are in place, I would like to actually stop. I would like to don't continue and sorting the checking the rest of the items. So now the question is that how can I make sure that I know the rest of the items are in their place and everything is sorted? One thing that I can check here is that in the fifth step, if you try to bubble up the fifth largest item, you can see that by comparing every item at index I and I+1, you wouldn't do any swap, right? All the items are in place and you would never get this condition true. If you never get this condition true, it means that every item is in place. Always the item at index I is smaller than the item at index I+1. So all the items are already sorted and I can stop. How can I check that? I can modify this sorting algorithm by adding a Boolean variable. I'm calling it actually is sorted. I would initialize this variable as false, and every time that I'm going to actually, before this loop, always initialize the is sorted to be true, and I would actually check that inside the loop, whenever I do one swap, whenever this condition became true, I would change the is sorted to false. Okay, so before the loop, I would initialize it as true. I just wanted to make sure that if only once this condition became true, it means that yes, there is some unsorted, at least there is one unsorted pair. Okay, if there is no unsorted pair, everything is correct and in place. So if this condition became true, I would change the is sorted to false. But if you never get this condition true, this condition is always false, it tells you that everything is in place. So in that case, is sorted will remain true. If is sorted is true, the outer loop will stop. The outer loop will you can say that I have added this condition to the outer loop, so the outer loop will stop. Now let me actually show you that what is going to happen for the best case of this algorithm. What if the input that you pass to this sorting algorithm to sort has all the items already sorted? Something like this. So you can see that this loop will start is sorted, will be initialized as true. This loop will iterate, but you can see that this condition will never get true. If you check every item is smaller than the next item. So every index I is smaller than every index I plus 1, right? So this condition will never be true. So after the complete iteration of this inner loop, you will see that when j is equal to 0, the loop will iterate. When j is equal to 1, what would happen to this condition? You will see that is sorted is still true, so this condition will be false, and so the outer loop will stop. So yes, now the best case time complexity will change to linear, and the best scenario is that if the given input is already sorted, bubble sort is smart enough to stop after the one iteration of the outer loop. After just one iteration of the outer loop, the bubble sort will stop and won't actually iterate and sort anymore. So the best time complexity is going to be linear. How about the worst case? The worst time complexity is when the input is sorted but in a reverse order. 7, 6, 5, 3, 4, 3, 2, 1, and 0. If the input is reversed is already sorted but in reverse order, in the first iteration, the largest item needs to be actually swapped until it actually reached to here. In the second iteration, the next largest, and you actually iterate over all the possible cases. So the worst case is still going to be n power 2. So what would happen for the average case? You can see that if you randomly give an item, the number, you can actually just argue that in the average case, the inner, for example, you can say that in the average case, the outer loop, or you can say that over the inner loop, the loop will iterate, for example, for half of it. Although it iterates for the half of it, but still it actually makes the time complexity of n power 2 divided by 2. So still the average case is going to be n power 2. So this is going to be the summary of the bubble sort. The time complexity of the worst case is n power 2, average case is n power 2, and the best case is linear, which is when the array is already sorted, or for example, there is just a small number of unsorted pairs that after you fix them, everything will be sorted and the algorithm will stop. And a good thing about this sorting algorithm is that this is in place. You don't need some additional array. I think this is quite clear from the algorithm that we discussed. You don't need to use additional array. You sort all the items in place. So this is the summary of the bubble sort. The next sorting algorithm that we discussed is insertion sort. So the idea of the insertion sort is that, for example, assume I have already sorted. The idea is a kind of, a recursive idea, although the algorithm is not recursive at all. So just assume that this part of the array is already sorted. If I wanted to, increase the sorted part, the thing is that you could actually just think about it in this way, that the next item is going to be some item that I don't know the value of that. I just need to just compare it from the largest item to down and find the correct position for this item and put the item there. So this is going to be actually the procedure, that how you insert 14 inside a part of the array which is already sorted. So you compare 14 with the item 40. If it is a smaller, you swap them. Yes, it is a smaller. You compare it with the next item. If it is a smaller, you swap. And you continue. Compare the item with the next item, and you continue until you find the position that 14 is not smaller than the previous item. Whenever it is not smaller, you can stop. Why? Because you already know that everything was already sorted. So everything before 12 are already smaller than 12. I don't need to actually do anything else. 14 is at its position. And you see that in each of these steps, basically one item will be shifted to the right and 14 will be shifted to the left, right? By this swapping at every step, you are just shifting. It's just like you are shifting 14 down until it finds its correct position, and then you would stop. So this is the whole algorithm. Just one modification that you can do, this loop that here, you can see that this loop is basically showing just one step, that you started, for example, at index k. This is at index k, and you want to find the correct position for this item, put it there. Instead of, in fact, swapping 14 and 40, and then 14 and 33, and then 14 and 26, what I can do is that I would put the item at index array inside some temporary variable, and instead of swapping here in the body of this loop, instead of swapping, I will just shift the item. So you compare always, you started from index j equal to k, and you continue until the temporary variable, which is basically here for the is going to be the value 14, until it is actually smaller than the value at index j minus 1. It is just like you wanted to shift the value at j minus 1 and put it at index j. Okay, so it's just like you are shifting 40 to index k. Then you will shift 33 to index k minus 1. Then you shift 26, 21, 15, and 12, and 19, and then you would stop, right? And then put 14 at its correct position. So this part is out of the loop. So the only thing here is that the trick is, instead of swapping, I would just shift. Why I would do that? Because you can see that swap needs 3 statements. If I am swapping 2 indexes, index at j and j, for example, minus 1, you are swapping these 2, right? You need 3 statement. For example, temp equal to a index j, then a index j equal to a index j minus 1, then a index j minus 1 equal to. So if I am doing one swap, I need 3 statements. But if I am doing a shift, I just need 1 statement. You would actually say that it doesn't change the the time complexity, asymptotic analysis of the time complexity, that is totally correct. This change is not going to, this modification is not going to change the time complexity. Whatever is the time complexity, that would remain, but it helps me to get whatever is the time complexity. If the time complexity is, for example, t of n, whatever it is, using the swap, this is going to be t of n almost divided by 3. This is going to definitely be better, right? In terms of, in practice, definitely this implementation is better than using the swap. So this is going to be the full algorithm. This is the inner part, okay? That I put the array at index k as a temporary variable, and this is actually the loop that I just discussed. I need to just put an additional array outside which actually iterates from k equal to 1 to the end of the list. Okay, so basically it tells you that over the array, we would first assume that, okay, the first index is already sorted. In the second iteration, you would assume that these two, so this part is iterated, is already sorted, and you wanted to actually insert this item in the sorted, already sorted part of the array. So what is the time complexity here? So it is clear that the outer loop will iterate n minus 1 times, right? It starts from k equal to 1, and it goes until the length of the list. So the outer loop will iterate n minus 1 time. How about the inner loop? The inner loop will iterate from j equal to k to until j is greater than 0 and j minus 1. So if you don't care about this part, the inner loop will definitely iterate, depending on what is the outer loop, will iterate k times. Okay, so where k is equal to, at first it is equal to 0, 1, 2. So this is going to be again this summation of 0 iteration plus 1 plus 2 until n minus 1 iteration, which in total is going to be the summation of I equal to 0 to n minus 1, which is going to be n to n minus 1 divided by 2. This is going to be theta of n power 2, right? But I have a part of this, actually this condition. This condition will stop the loop. So that's why it actually makes the worst case and best case different in the case of the insertion sort. So now you can see that if the input array is already sorted, okay, if your input is already sorted, something like this, nothing will stop the outer loop to iterate. But how about the inner loop? So the outer loop will always iterate, but how many times the inner loop will iterate? So when k is equal to 1, okay, so the temporary item is going to be, temp is going to be equal to, for example, this value 1, and the inner loop won't iterate, right? Because the value of temporary is already greater than the value at index j minus 1, which is going to be 0. So you don't have to shift. So the inner loop won't iterate. For the second iteration, when k is equal to 2, temp will be equal to 2, right, this item, again, the inner loop won't iterate. Now you can see that if the given input is already sorted, the inner loop would never iterate. And because of that, the total time complexity for the best case is going to be linear, because only the outer loop will iterate, but you would never actually swap or shift anything. So the time complexity for the best case is going to be linear. But how about the worst case? The worst case time complexity is when the items are sorted in reverse order. In that case, always the item that you are going to put is going to be the smallest item. So something like this. So when you are going to insert 4, 4 is smaller than 5, so you have to swap. You have to shift actually and put the item in its correct position. 4, 5, 3, 2, 1. And then when you are actually going to insert 3, you have to shift all the items to the right to put 3 at the smallest index. Then in the next round, you have to shift all the items to the right to put 2 as the smallest item. Then you would shift all the items to the right to put 1 at the smallest index. Okay, so the inner loop will iterate always, the outer loop will always iterate, so the time complexity of the worst case is going to be n power 2. And again, on average, this is going to be n power 2 as well, because you can just argue that on the average, always the inner loop will iterate, for example, half of it. So that is going to be the summation of, for example, if n, the size of the list is n, you will iterate, for example, 0 times, 1 time, 2 times, until n divided by 2 times. The summation of all these numbers at the end is going to be theta of n power 2. So on average, still the time complexity of the insertion sort is going to be n power 2, but in the best case, this is going to be linear. I can also actually argue here that if you look at the sorting algorithm, it is clear that insertion sort is very simple to write. It doesn't use additional array. And so it does the sorting in place. So it doesn't actually use, it basically just use 2 indexes k and j and some temporary variable tmp, nothing else. The good thing about the insertion sort is that, as I mentioned before, the insertion sort is going to be one of the fastest sorting algorithms if the input size is small. If the input size is large, you will see that n power 2 is way smaller than n square, n log n. So if I get a sorting algorithm like quicksort, which works in n log n compared to n power 2, if the size of the input is something like 8 million, 8 million is not really big in terms of the computer science, especially nowadays. If you run the quicksort, your sorting algorithm would take only 4 seconds, although if you run the insertion sort, it would take, around 1 day to sort the, an array of size 8 million. So there is a big difference between 1 day and just 4 seconds. Of course, we prefer quicksort and the sorting algorithms that works in n log n. So in the next round, I'm going to discuss about the sorting algorithms that works in n log n.